Hello, everyone, and welcome back to another Planetarium show. My name is Jessica. I'm the director of the Planetarium, and with me tonight is one of our students who I will let introduce himself.
Hi there, my name is Eli. I'm a physics and astronomy student at UMD.
So, tonight's show is a pretty cool one. It's going to take a look at things that we typically think of as just facts, but obviously we had to figure it out and learn it at some point. And so, Eli is going to walk us through some of these things and how we actually figured out these known facts that most people don't really think about, like the speed of light, for example. Now, as always, if you have any questions throughout the show, feel free to leave them down in the comments. I will keep an eye out for those and we'll let Eli know as those questions come up. We'll also have time at the end for questions as well. So I guess with that, Eli, I'm going to turn it over to you.
Awesome. Okay. As usual, I have to make sure the window looks good.
I
Uh,
actually remember to set screen share this time beforehand.
awesome. Um,
A year and a half later, I'm learning, folks.
how does that look?
Small,
How about now?
much better.
Okay, sweet. Okay, so welcome to How Do We Know? To start, this is probably the most boring part of the show, but we do need to just give a little bit of mathematical context, so what I'm saying isn't complete gibberish. Um, a lot of these early discoveries and advancements in astronomy and physics are largely due to trigonometry, which was one of the predominant mathematics at the period because things like calculus hadn't really hit the scene yet. This does kind of look disgusting, and I agree with you. But so the general idea is that we have this right triangle right here. Is my cursor? Can you see it, Jessica? Okay, sweet. So we have this right triangle right here, and there are three sides to a right triangle. You have the hypotenuse, which is the longest side. You have the adjacent line, and these aren't, they're just for the sake of the trigonometry. You have the adjacent line, and that is in terms of this angle right here. We call that theta. So this line is adjacent to that corner, that angle, and this line is opposite to that angle because it's on the opposite side of the triangle. So there are a couple of functions or kind of equations that you can work with to figure out either what this angle is, how many degrees it is, or how long the sides of the triangle are. The first one is the sine function, which is the length of this side divided by the length of this side, or in other terms, the length of the opposite side divided by the length of the hypotenuse, equals the sine of this angle, which is just a number. Sine of that angle is just a number, and it's just a ratio. The cosine is the adjacent side divided by the hypotenuse, and the tangent is the opposite side divided by the adjacent side. And again, those are all ratios, just a number like 0.6 or something like that. So and this is kind of some context down here. So say the opposite side were 1 unit long and the adjacent side or the hypotenuse was 2 units long. That would you could use that. You could take what's called the inverse function of sine and put 1/2 into it to learn what this angle is, and you would get 30 degrees. I don't know if I explained that. Jessica, did that make sense? Is
Yep,
there enough context there? Okay,
I think
cool.
you're good.
Awesome. So probably won't really need to know this, but I just wanted to give some context for what I'll be talking about. So the first thing we're going to talk about is how we know the size of the Earth. The size of the Earth is pretty well known nowadays. We have it down pretty accurately, but that is due largely in part to the advent of space telescopes and their ability to take images of the Earth. Previous to this, however, when we did not have space telescopes, it took some very clever experimentation around 250 BC by Greek astronomer and scientist Eratosthenes, excuse me, to get a good idea for just how big the Earth was. He knew that on the day of the summer solstice, the sun cast no shadow at noon in the city of Syene, which means that Syene right here lies directly on the Tropic of Cancer. he wanted to see if the same could be observed in Alexandria, and I'm missing an I right here. I'm just noticing, not Alexandria, Alexandria, which is a city quite some distance away from Syene. So he traveled to Alexandria and he put a post in the ground to see if a shadow was cast. To his surprise, a shadow did appear, which means that the Earth is not flat. And it measured to be about 7.2 degrees off of the post. Now, if we treat this ray of light as if it's a parallel line to this line right here, which you could think of as the post going into the ground in Syene, that means that the angle cast by the shadow in Alexandria is equal to the angle between Syene and Alexandria. So that means that Syene and Alexandria are 7.2 degrees apart on the circumference of the Earth. If they're 7.2 degrees apart and 7.2 is 1/50th of their circumference, as every circle is 360 degrees circumference, that means that the distance between Syene and Alexandria is 1/50th of their circumference, or the length of, or the total. What's a good way to describe circumference? The length.
The distance of the circle around the Earth.
Yeah, there we go. Thank you. He figured out that the distance between Syene and Alexandria is 1/50th of that distance. So he actually hired someone to literally walk from Syene to Alexandria, and he figured out that the distance between Syene and Alexandria is about 800 kilometers. So multiplying 800 by 50, he found the circumference of the Earth to be 80,000 kilometers, which is super close. It's just under 1% off from the real value of 80,060 kilometers. So that's amazing, especially for the time period. That degree of accuracy is almost jarring. So hats off to Aristophanes.
What I find really funny, though, is like at the time, no one believed him.
No.
Because his value was different than what Aristotle calculated using the shadow of the Earth during a lunar eclipse.
Yep.
Aristotle's value was like half the size of the actual Earth.
Mm-hmm.
Even though Aristophanes was much more accurate, no one believed him because he disagreed with Aristotle, and Aristotle's reputation meant no one questioned him.
Right.
So like he didn't get the kudos that he very rightfully deserved until much, much later.
Which happens a lot with this kind of thing. Like, I feel like
Yeah.
a lot of people have gotten, yeah, it's unfortunate. So the next thing we're going to talk about is the size of the moon. So the size of the moon was figured out by Aristarchus of Samos at about the same time. So knowing the size of the Earth was an invaluable tool in calculating other things. And Aristarchus correctly reasoned that a lunar eclipse was a result of the Earth casting a shadow onto the moon, but incorrectly reasoned that the sun's light reaches the Earth in perfectly parallel lines, as if it were this diagram. What actually happens is the shadow kind of narrows out the further it gets from Earth. So that causes a little bit of a discrepancy here, but still his reasoning was pretty solid, just a little mishap there. So in order to find the size of the moon, Aristarchus first timed the period in which the moon was within the Earth's shadow. So how long it took for the moon to enter and leave the shadow casted by Earth during a lunar eclipse. And that is about 2.6 hours. Then he timed the period it took for the moon to travel one of its own diameters in the sky. So imagine you place two of the moon directly next to each other. However long it took for the moon to move from one to the one right next to it. That's the next thing he measured. And he found that since it took the moon 2.6 times longer, because that takes the moon about an hour. Sorry about that. He reasoned that since it took the moon 2.6 times longer to travel the size of the Earth than itself, the Earth must be 2.6 times bigger than the moon. And he found the diameter of the moon to be about 38% of the Earth's. Now, again, there was the discrepancy of how the shadow is cast, and that resulted in about an 8% discrepancy. But again, remarkably close, much better than anyone else was doing. So Aristarchus found that it was 38% of the Earth's size, when in reality it's about 29 to 30. So again, pretty amazing. A little bit of a discrepancy that we figured out later on, but for the intents and purposes of that time period, it was pretty close. So After Aristarchus discovered the size of the moon, Hipparchus used this as a stepping stone towards discovering the distance to the moon from the Earth, which is also a very important measurement. This one is probably the most mathematically intensive and absolutely impressive. And it's again, it's jarring. I have to remind myself that this happened over 2,000 years ago, when they were still using, like, I actually don't know if they were using these, but I was going to say slide rules. But like, what are the ones with the beads that you have to like move across the?
Oh, oh my God! I just had this word in my head like 30 seconds ago until you asked.
What are they
Abacus.
called? Abacus, yes. Yeah. And so they were using stuff like that and poles in the ground to cast shadows. So to find, well, actually, it's pretty smart. I shouldn't talk bad about it. So to find this distance, Hipparchus realized that as you move across the surface of the Earth, the apparent position of the moon in the sky changes relative to the stars behind it. So you can see in this image here, you've got these two stars right there. And then if you were to walk a fairly large distance across the surface of the Earth, they would then appear to be there after that walk. So this is extremely useful in finding the distance, and you're using something called the parallax method, which is still used in astronomy today. Not exactly like this, but for other things. In this method, you create an imaginary triangle between these two apparent positions of these stars and solve it to find the distance. So this is a diagram. So you have the two apparent positions of the star. So imagine you have one star next to the moon. You walked across the surface of the Earth. It appeared to move in the sky. You have these two apparent positions of the stars. And if you connect them with the moon and then continue the triangle outwards, you will find this triangle right here. Hipparchus found this angle to be 0.3 degrees. And he did that by measuring the distance between the stars in the sky. So he found this angle to be 0.3 degrees. And he also knew the distance between Chelsea in the United Kingdom and Athens, Greece, which are the locations from which he looked at the star relative to the moon. So say one is Chelsea and two is Athens. So by doing some trigonometry and solving the triangle like we saw in that math dump earlier, he found the distance to the moon to within 17% of the actual value. Again, not super precise, but pretty impressive for the time.
And
So
another fact in there, Hipparchus actually invented trig.
yeah,
So like he invented the mathematics used in this method.
right.
Like I mind blown. Like these guys were so smart.
Yeah, and like the thing that I always think of is like I think about doing trig and I think about putting it in my calculator, and it's like, oh yeah, they had to do that by hand and like just figure it out. It's
Yeah, there
kind of
was a lot of like memorizing of like tables
yeah,
and
yep.
things. Yeah.
Because the way they did it back then is they would actually like set up a triangle and measure the angle and then find the ratio. So then they knew like, oh, if the sides are this long, then it's this number or something like that. So then they just had like a table of values for certain things, and they just had to memorize it to do that math. It's frightening. So like I said, this method lives on, and stellar parallax is one of the methods used to find the distance to faraway stars. Rather than the moon being the target in the diagram above, they replace it with a star, and since the distances are much larger on that scale, the two positions used to measure the change of position relative to the background of the star are at the opposite ends of Earth's orbit around the sun, rather than two locations on the Earth's surface. But you use the same idea. See how much its position in the sky appears to change relative to its background. And knowing the distance across Earth's orbit, you can make that triangle again and solve it for how far that star is. How do we know the distance to the sun? This one's pretty cool too. So after this, Aristarchus took the reins again after Hipparchus and wanted to use the distance to the moon to find the distance to the sun. Like all others before him, he used trigonometry and triangle identities to his advantage and constructed a right triangle out of the Sun, Earth, Moon system when the moon was in its last quarter phase, which means that the Sun, Earth, and Moon are making a almost right degree triangle with each other. He then had to estimate the angle between the moon and the sun in the sky with his naked eye, which he estimated to within 3 degrees of the accepted value. I don't even know how you do that. but he did it, and he estimated 87, while the actual value is about 89.93 at that point. So from here, he used the cosine function and arranged it to solve for the distance to the sun and got an answer within 14% accuracy. So as you can see, what he did here is he estimated the angle to be 87 for the correct number. We're going to use the correct value, 89.93. But imagine he put 87 right here. He knows the distance to the moon because Hipparchus figured that out. And now he's going to solve for the distance to the sun. And to do that, he multiplied the distance to the sun to the other side, divided the distance to the moon by the cosine of 89.93 or 87, and found it to within 14% accuracy. So again, amazing. The next thing we'll talk about is how do we know how big the sun is? This discovery, another incredibly impressive one, comes about only because we live in perfect alignment such that when the moon passes in between us and the sun, it blocks the sun almost perfectly. If the Earth were any closer or further from the moon or sun, this method wouldn't work, and it would have been much harder to solve this problem. Luckily for us, however, the alignment is just right. And after finding the distance to the sun, Aristarchus thought that he could use this perfect alignment to his advantage. He drew a diagram, not unlike the one seen on the top right here, and realized that the moon and the sun had the same angular size in the sky. Because of this, Aristarchus found that we could apply some rules we know to be true about similar triangles, and discovered that the size of the sun could be found through the ratio shown below the diagram. So what he means by the same angular size is during an eclipse, if you were to look at the Earth and at the moon and the sun, they appear to be the same size in the sky. We know that they're not the same size, but from our perspective, they are almost perfectly the same size because the moon is so much closer and so much smaller. So knowing this, he used this ratio down here on the bottom right. So the size of the sun divided by the size of the moon, which is just a ratio, is going to be equal to the distance to the sun divided by the distance to the moon. And that's because we know some things about similar triangles. The similar triangles in this case would be this one, this triangle right here. So this is the moon, this is the sun. This triangle and this triangle. So those are called similar triangles, and he used that to find the size of the sun. Well, his estimate was off by partially a significant amount, which is due to some of the discrepancies from the earlier measurements. He still found a reasonable estimate for the sizes of the Earth, Moon, Sun system, and these discoveries led to some pretty groundbreaking theories and discoveries about space, namely that the Earth orbits the sun, which was pretty important in astronomy. This next one is absolutely my favorite. I actually wrote a report on this one for one of my sophomore classes. The next discovery is pretty awesome because it happened almost completely on accident. So some 1500 years after the time of Aristarchus and Hipparchus, the first attempt to prove that light travels at a finite speed was by Galileo Galilei, who is not who you're seeing on the side. I'll get to that in a minute. But Galileo's experiment consisted of two men with lanterns standing on hilltops separated by less than a mile. You can probably guess how that turned out. What they attempted to do was they were standing on opposite sides. One person would open the lantern, and as soon as the other person saw that lantern, they would open their lantern. And they would see how long did it take for the initial person to see the second person's lantern, and that would give you an idea of how fast light travels. There are a lot of errors with that methodology, namely the time to open the lantern is going to be significantly more than the time it is for the light to travel that distance, but they didn't know that at that time. But like, you know, just by being in your house, like flick a light switch, it's almost instant, and that's because light travels so fast. So that experiment was kind of destined to fail. But Ole Romer, who you're seeing on the left, was actually not attempting to prove this when he was conducting this experiment. And the experiment was that he wanted to measure the time it took for Jupiter's moon Io to orbit the planet once. He just happened to stumble upon the speed of light by accident, which is kind of funny. So he noticed that when the Earth was at its farthest distance from Jupiter, the orbit of Io appeared to be about 11 minutes longer than the average orbital period that he found. When it was at its closest distance, it was 11 minutes shorter. He reasoned that this was due to the fact that the light coming from Io traveled at a finite speed, and this discrepancy was due to the travel time it took for the light to reach Earth at those different points. And from there, famous astronomer Christian Huygens, who, if I remember correctly, the anniversary of his death was a week ago, 2 weeks ago. But Christian Huygens measured the speed of light and found it to within 70% accuracy. So again, not super close, but extremely impressive given the technology at the time, and absolutely groundbreaking in physics and astronomy to know, like, even within 70% accuracy, how fast light travels. Nevertheless, the speed was confirmed with much more accuracy 50 years later by the astronomer James Bradley. He conducted a different experiment that it's very complex. I don't even quite understand it very well. But again, Huygens' number was confirmed, which is very cool and impressive. Okay, so this is going to touch back on that parallax method that we talked about. How do we know the distance to nearby stars? So we remember how Hipparchus used the parallax to find the distance to the moon. That is its position change relative to its background. This method is used to find the distance to nearby stars, like I said, called stellar parallax. This is just kind of a diagram of what I was talking about before. So you have your target star, you want to know how far away that star is, and you have a background behind it. So at one end of Earth's orbit around the sun, you see it like this image right here, because you're looking at it, from this relative viewpoint, and it appears that the star is right here. 6 months later, when the Earth is halfway through its orbit, you look at it this way, and you see that the star appears to be right here because you're looking at it from a different angle. Just like Hipparchus, you can set up some triangles, solve it using trigonometry, and find the distance to that star, which is literally how it's done today for a lot of stars. So it does take a little while, it takes 6 months to get this measurement done. But thankfully, we got a lot of time. We got time because if you think about it, on this orbit, you can look at a lot of stars during this 6 months. You can kind of continuously do it as you're going around the sun. So pretty interesting. This is another one I really like because I like galaxies. For distances much larger than stars within our galaxies, like the distance between galaxies, parallax doesn't work, as the parallax angle made by Earth orbiting the sun is just too small. The numbers get too hard to work with, and it just doesn't really work. Instead, astronomers rely on things called standard candles. Standard candles are any stars or events that have like a known and definite brightness and can be identified from far away. A really good example of these is type IA supernovas. That's right, Jessica. IA.
1A.
1A. Sorry, yeah, 1A. That's the white dwarf supernovas.
Yeah, that's the white dwarf.
Yeah. So when white dwarfs, and Jessica, you might have to correct me if I'm not remembering it right, but when white dwarfs subsume or like come into contact with other massive objects, it can cause a supernova because the white dwarf gains enough mass to cause a supernova, and it's like a pretty definite brightness. We know how bright those are. I mean, they're about the same brightness every time. So if we know how bright it is, and we take into account the inverse square law, which is this equation right here, and it looks very simple because it is, the brightness of an event or object decreases with an inverse square proportionality as you move away from it. So if you're twice as far from something, it's 1/4 as bright. If you're 4 times as far, you're 1/16. It's 1/16 as bright. So if you're looking at a light bulb from a foot away and it's X brightness, and then you move another foot away, so you're 2 feet away or twice as far away, it'll be X over 4 as bright. So that's what that means for context. So
Which,
if we look
just to give a little bit more, like, this is a relationship you probably know inherently. Like, this is
yeah,
something we notice and see in our everyday life, but now you know the actual math behind it, the mathematical relation, which I think is always cool to be able to bring in those like everyday experiences and see exactly what's going on.
right. Yeah, so it's a super powerful tool that we see every day. So if we know how bright this event is, this supernova, and we're looking at a galaxy and we see that event happen in that galaxy, and we can measure how bright it is, we can just solve this for the distance and figure out how far that galaxy is, which is a really cool tool because galaxies are pretty far away, and it's cool to figure out how we know their position so accurately. And I just really like galaxies. I'm a galaxy nerd. So the last thing we're going to talk about, I think it's the last thing. Yep. We're going to talk about how we know where black holes are. something that's like glossed over when we're talking about black holes is how we detect them sometimes, because black holes are really inherently interesting. You talk about the weird stuff that happens around them and what a black hole even is, but finding them is actually a pretty arduous process. If you think about it, a black hole is fundamentally really hard to find because it gives us no light. So we don't, well, no visible light at least, and it's really hard to pick out the light that they do put off, or the material around them puts off. So this means we have to often identify them with context clues. um, Black holes are pretty commonly found by observing the things around them. So if we watch this video, it appears that the stars around this invisible object are orbiting a very massive object. They're moving around something that is obviously very heavy. In a period of 10 years, it pulled multiple stars around with extreme ferocity, which is a lot of movement for a star. Um, there's only one thing we know of that could whip stars around that fast, and in this case, it is the black hole at the center of the Milky Way, which is called Sagittarius A star. Its extreme gravitational influence is pulling the stars around it in very volatile orbits, and it is through this footage that scientists were able to infer the existence of the black hole there. So you can see there isn't anything where the reticle is, but the stars around it are moving very fast. You can see this is the timeline up here. I'm sorry, I keep bringing the title up. You can see that those stars are moving massive distances in very short periods of time. And so it can be inferred that, here, let me bring it back. It can be inferred that at this reticle right here, there is a very massive object that doesn't put off any light that pulls stars around it very fast. The only thing we know of that does that is black holes. So that's how we find black holes a lot of the time. There are other ways to do it, but that is one of the most popular ways. And with that, I am out of material. So
Very awesome. So we do have a couple questions, which not surprisingly were triggered by black holes.
yep.
That always gets us questions. Um, so first, which actually isn't related to black holes, is there sound in space?
No, because sound, just like light is a wave, but sound needs a medium to travel through. So like when I'm in my room and I tap my desk, the motion of me tapping my desk and the desk moving after I tap it causes the air around it to move, and then those waves perpetuate through the air and fill this room and go into the other room. And when they hit your eardrum, they vibrate your eardrum and your brain turns that into sound. So if there's no air in space for those waves to travel through, they don't go anywhere, and there's nothing to hit your eardrum. So no, there's no sound in space.
Yep.
So whenever you watch science fiction movies and something blows up and it makes a huge explosion sound.
That is wrong.
Nope.
So the other question is black holes. And so a follow-up to is there sound in space is do black holes make sound? And that's an interesting question because black holes can be surrounded by a very dense disk of gas, which would be a medium for sound waves to travel through. So within the accretion disk of a black hole, you could have sound travel. And I guess the black hole isn't inherently creating the sound, but the gravitational pull on the material in the accretion disk can maybe trigger some sound. But you'd have to get close enough to be within the disk, which is like the tens of thousands of degrees temperature, which you don't want to be in, or you also don't want to be next to a black hole. So I guess theoretically, in the right circumstances, yes, but it's not something we ever actually want to experience.
Right. The only other thing I can think to add to that is we can kind of make sound out of gravitational waves, which black holes create. Like we can transfer we can represent the motion of those gravitational waves that perpetuate outwards from black holes or black hole collisions into a sound. And we've heard it before, except when we heard it, it was neutron stars, I think. Remember the one in 2019? They saw like the two neutron stars collide.
Oh, yeah.
It was like it. I don't want to make the sound and sound stupid, but
it's like a chirp.
Yeah. It started as like a low, like whoa, 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 and then it like sped up and increased in pitch, and then when they collided, it just like whoop, and then that was it.
But that's
And
not necessarily, that's not sound waves itself. It's taking a
no,
different kind of wave and changing how we perceive it to be, if we were to perceive it as sound, this is
right,
what it would sound like. We also do the same thing with light.
yeah, that's what your radio does. It just turns light into sound.
Yeah. But also like pictures and stuff. It's, what is it, like the sonification of images.
Yeah, those are super cool. They'll like take a picture of a star field and like every color is a pitch. And so
Hmm.
then like encounters a star that's a color, it makes that pitch and they like make little songs out of it. It's pretty cool.
Yeah, that's really cool. But
NASA has them. I just made a post with one of those like, well, I actually time kind of has no meaning right now, but I would say within the last month. Um, but yeah,
yeah,
but no,
pretty
no
cool.
sound.
All right. Well, if there are any other questions, go ahead and leave them in the comments. We'll take a few more minutes to see if any more of those come in. And while we wait, let me tell you a little bit about what's coming up over the next week. So on Saturday, Lindsay is going to be here to tell us all about the history of spaceflight, which is a look at the amazing women who are largely responsible for humans leaving the Earth and even just sending spacecraft out to explore our solar system. There were a lot of women who did work that was invaluable to this, but are often overlooked. So we're trying to change that with this show. Next Wednesday, Eli will be back again to tell us all about the scale and wonders of the universe. If you've ever wondered exactly how big is our universe, we're going to try and answer that for you. And then next Saturday is the next edition of our exploration series, where we're going to take a look at space junk. So things like meteoroids, asteroids, and comets, what exactly they are, where they came from, what we can learn from them. And we specifically picked this topic because we are coming up on one of the biggest meteor showers of the year. So this will allow us to kind of talk a little bit about where some of that stuff comes from that we see in meteor showers. One other thing, we finally have the details for our Dark Sky Caravan for this year. So it's going to run August 9th through 14th. The first 2 days, the Monday and Tuesday, August 9th and 10th, are going to be virtual shows here on Facebook Live. And then starting on Wednesday, we're going to pack up our telescopes and head off to a few different locations to do some star parties. So our first night will be in Duluth. We'll actually be in the parking lot outside of the planetarium, which I think we have finally managed to convince them to turn the parking lot lights off so we won't have those interfering, which is going to be fantastic. But we're also doing it there because we want to bring some of you in for a show. So we're also going to be running some small group shows during that time period as well. We are limited in space. You can find details and everything on the website for how often those are going to run and space limits and all of that. After that, we're going to head to Taguchi State Park on Thursday. Friday, we're going to be up in Grand Marais, set up at the North House Folk School. And then Saturday, we'll be at our darkest location up at the end of the Gunflint Trail at Chickawauk Museum and Nature Center. We are so excited to be heading back out and doing this. I cannot wait, and I'm hoping, fingers crossed, that the smoke clears out by then so that we can have some beautiful skies. That's also going to be the week of the peak of the Perseid, so we should have hopefully some awesome meteor showers during our dark sky adventure. And yeah, we're excited to get back out there. And you can find all of the details on our website. I have it linked in the video description to get directly to that. So yeah, come out and join us. It's gonna be fun. All right. I'm not seeing any other questions. We did get told that the two of us are awesome. Thank you. We appreciate it. We definitely have fun doing these.
Or
All right. Well, I guess we will wrap it up there. So thank you everyone for joining us. We hope you have a wonderful rest of your evening, and we will see you again next time. Bye.